Welcome to Plutus IAS, and today we are starting with the oxidation mechanism for using ScO₂. Now, ScO₂ is part of your UPSC syllabus paper 2, where in the synthetic use and preparation of reagents. Now, ScO₂ is used for various purposes, majority for your allylic oxidation towards the less sterically hindered side, and also for your alpha carbons which are adjacent to your carbonyl carbons. It is used to either use for hydroxylation and to convert the adjacent alpha carbons on the carbonyl either to an aldehyde or a ketone depending on what type of group you have. Now, majority of the cases, the question that are asked in ScO₂, normal cases, there are two cases in which the question regarding ScO₂ can be asked. First question can be asked that you are given a reaction, you are given the reagent, you are given the product, and the examiner asks what type of reagent that you are using. So it's highly necessary that we should understand completely what are the functions of ScO₂, how does it function, and what are the cases in which it can function, and where it cannot function. First part. Second part, you are given a reagent and you need to do the conversion in the mechanism process to obtain a definite product. So these are some cases in which ScO₂ can be asked. So we can say that it's a very important reagent. So now let's move towards the mechanism. The mechanism of ScO₂ is a three-step mechanism. It consists of a three-step mechanism, and in the mechanism, the first two steps involve your sigma-tropic rearrangements. And step number 3 will involve the hydrolysis. The sigma-tropic rearrangement that will be seen in the step number 1 will be 1,5 sigma-tropic rearrangement, and in step 2 it will be 2,3 sigma-tropic rearrangement. It is the step 2 that decides how ScO₂ is working for the reaction and which site will be selected for hydroxylation. It is decided by this second step of the reaction, which is responsible for the stereospecificity or the selectivity of the position around a double bond. Now, the step number 1 refers to your ene reaction. Ene reaction in which you will add ScO₂ to the alkene. It will get added to the alkene, and then we'll see 1,5 sigma-tropic shift to give us selenic acid. Now, for example, let's say we have this particular alkene, SeO₂. Now, let's start marking. This will be 1, 2, 3, 4, and 5. So, while making of the mechanism, it's very important that you understand how you are marking these positions. These markings will decide what type of a rearrangement you are marking. So, first position, wait. Ene. So first, it will be the ene reaction. So what happens is, this oxygen will take the pi bond electrons from ScO₂ and attack the alpha position hydrogen which is present here. Okay, and it will attack this hydrogen, and this pi bond will attack this compound, this SeO₂. Here it will form SeOH, double bond O, and the double bond will be formed here. This is called as your selenic acid. In your exams, whenever you write the mechanism, please always mention the important stages of the reaction and the important compound that you are getting. So in the first step, we have seen what? The ene reaction. And ene reaction is what? Addition of ScO₂ to the alkene along with 1,5 sigma-tropic shift to give you selenic acid. Now, step number 2 refers for the formation of the cyclic transition state and for the 2,3 sigmatropic rearrangement. So we have our compound SeO₂. Now the double bond is here. Now in this step we'll have a formation of the cyclic transition state along with 2,3 sigmatropic shift. On the arrows always mention what you are doing in the reaction. Sigmatropic rearrangement. So here what will happen? Again marking the position. This is position number 1, that's position number 2, and that's position number 3. So the double bond will shift its place from what? Carbon number 2 to from 2,3 to 1 to where? This oxygen will attack this in the position number 3 and will have new compound which will look like this, which is SeOH. This is called as your selenate ester. Selenate ester. Then in the first step we will hydrolyze it. Wait, I made one carbon less. Carbon 1, carbon 2, carbon 3. That's selenate ester. SeOH on hydrolysis. On hydrolysis we'll have what? H plus and OH minus. In this step the hydrolysis will occur and at the allylic position we'll have now the OH attached to it with selenium hydroxide as the byproduct. So what will happen? This oxygen will take electron, will attack the H plus, and this OH minus will attack selenium. So in this step you see that it is the cyclic transition state. This cyclic transition state requires a very specific arrangement of the SeO around the alkene to form this state, because of which we say that while using SeO₂, the hydroxylation around the double bond will always occur at the less sterically hindered side, because the less steric hindrance it will feel, the more it will be easier for the formation of the cyclic transition state. Hence, this will be the rate determining step. Sorry, not rate determining. This is the most important step that decides your selectivity of the SeO₂ and the position. So I hope this mechanism will be clear to you now. If you have any doubts, you can add it to the comment section and we'll see you in the next class. Thank you for joining us.